Greetings, sophomores. Welcome back to my physics dungeon. How you doing? Great. Thanks for asking. So, today we're going to start with when or under what conditions is energy for a single object not conserved? And the answer is when an outside force or a non-conservative force acts on it. Usually, the cause for energy in an object not being conserved is friction. So we're going to talk a little bit about friction today. We can still keep track of energy lost and attribute it to friction, and we can learn a little bit about friction in the process. So here's an example. A 4 kilogram box slides across the floor traveling 10 meters. If it started out going at 8 meters a second but slowed down to 3 meters per second, our question is, how strong was the force of friction that slowed it down? And to answer, we're going to use energy accounts. So there's a before and an after set of information. In the before, we have gravitational potential energy. The box is on the floor, so we'll say 0. We have kinetic energy, 1/2. The mass of the box is 4, and the speed is 8. So 8 squared. Before, we had 128 joules of kinetic energy. So the total energy before friction acted was 128 joules. After, because energy is conserved, we can instantly say that the total energy involved was 128 joules. After, we can also say that the gravitational potential energy is still 0 because the box is still on the floor. And we can say that the kinetic energy is half its mass times its new speed squared, and its new speed is 3. So we have 18 joules of kinetic energy. The object only has, in the after case, 18 joules of total energy. But the total energy in the system is still 128 joules. So where did that energy go? The energy was lost by the object. So we'll say energy has been lost. And it lost that energy to work done by friction. So we have a new category for energy in the after state here. It is that energy's been lost. Since the energy here is still a total energy, we can write an equation to figure out how much energy has been lost to friction. That equation looks like this. The kinetic energy plus the energy lost has to still be equal to the total energy. In this case, 18 joules plus the energy lost has to be equal to 128 joules. This means that the energy that was lost is 110 joules. That energy was lost to work done by friction, and the question here was, what was the force of friction that was slowing the box down? So we can find the force of friction now by saying that the energy lost is the work done by friction. And work is always a force times a distance. In this case, that force is the force of friction. In this case, the work is the energy that was lost, which is 110 joules. And the distance it lost that energy over was 10 meters. So the force of friction was 11 newtons. Here's another scenario where we can find out something about energy lost. In this case, there's a 30 kilogram child on a slide. And the child goes down the slide but comes to a stop after traveling 4 meters because there was friction. So friction brought the child to a stop. The question is, how far off the ground does she come to the stop? Again, we're going to do energy accounts to determine the answer. In this case, how far off the ground is, what is this height above ground level? So, we're going to separate this up into 2 locations, the top and the stop. At the top, the child has gravitational potential energy. It was a 30 kilogram child, M. We'll use 10 for gravity, at a height of 5 meters off the ground. 30 times 10 times 5 is 1,500 joules. At the top, the child was stationary and no energy had been lost, so the total energy of the child is 1,500 joules. When the force of friction brings the child to a stop at this lower height, we would say that the child still has gravitational potential energy of 30 times 10 times a height that we don't know. Because the child has been brought to a stop by friction, the kinetic energy of the child at that location is 0, and some amount of energy has been lost. The first thing we should have written down, because energy is conserved, is that the total energy in the system, which now includes the slide because of friction, had to have been, and is always, 1,500 joules. This energy lost is due to, again, work done by friction, and it's equal to the force of friction times the distance, which in this case, we were given. The force of friction is 150 newtons. The distance over which it acted was 4 meters. And so the energy lost due to friction was 600 joules. If we now pull out our energy account on the stop side, we can write that the gravitational potential energy plus the energy lost has to be equal to the total energy. This gravitational potential energy is 300 times the height. The energy lost, we just said, was 600 joules, and the total energy was 1,500. So we can find that the height that the child will stop at must be 3 meters. So apparently, this child is stranded 3 meters above the ground. Here's the last new content related to work, energy, or power, and it is power. We're going to revisit question number 7 from your workbook, which asked you to make this comparison. Person A pushed with a force of 100 newtons over a distance of 5 meters and took a time of 10 seconds to do the job, while person B pushed with a force of 50 newtons over a distance of 10 meters and a time of 7 seconds. And the question in number 7 that you've already answered by now was, who did more work? And the answer was neither. Neither person did more work because work is force times distance. And in this case, it's 100 times 5. So this person did 500 Newton meters or 500 joules of work. And person B did 50 times 10, which is again 500 Newton meters or 500 joules of work. So neither did more work, but the purpose of that question was not just related to work. It was also related to power. And if we asked a different question in the first place, which would be, who was more powerful we would get a different answer. Power is defined as work divided by time, or how much energy you expend per unit time. If you do the same job as someone else, but you do it faster, it means you are more powerful than that person. If we calculate the power for person A above, we see that their power was 500 joules per 10 seconds. This is 50 joules per second, or 50 watts of power. And that's the same watts that your light bulbs are labeled with. On the other hand, person B has a power of the same 500 joules, but in 7 seconds. This comes out to 71.4 joules per second, or 71.4 watts. This means that person B, in that instance, while they didn't do more work, they did the same amount of work in less time, which means that they were more powerful. Power is measured in watts, or joules per second. The unit watts is abbreviated W, capital W, after James Watt, who had a collection of horses. And he did experiments with the horses to see what kind of tasks they could accomplish in a particular amount of time. Because of this, there's a unit conversion that you may be familiar with. It is that there's such a unit for power as horsepower, and 1 horsepower is the same as 746 watts, or 0.746 kilowatts.